They called it the most advanced bomber in the world. And on the morning of November 27, 1944, Japanese technical intelligence officers stood on a muddy airfield in Manchuria, staring at proof. The Boeing B-29 Superfortress sat intact before them, its polished aluminum skin reflecting the weak winter sun. Serial number 42 to 6358, nicknamed Ramp Tramp, had made an emergency landing after a raid on Tokyo. The crew had escaped across the border into Soviet territory. The aircraft remained. Colonel Kikuo Nakajima of the Army Technical Research Institute approached the bomber slowly, as if the machine might suddenly vanish. He had seen wreckage before, twisted metal pulled from crash sites, fragments of American aircraft scattered across Chinese farmland. This was different. This was whole. The landing gear had collapsed on touchdown, but the fuselage was intact. The turrets remained in place. The bomb bay doors hung open, revealing the complex mechanisms inside. Everything about the aircraft seemed impossible. It measured 99 feet in length with a wingspan of 141 feet. The tail stood nearly 30 feet high. 4 Wright R-3000, 350 duplex Cyclone engines, each producing 2,200 horsepower, hung from the wings in nacelles larger than some fighter aircraft. The propellers alone were 16 feet in diameter. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Nakajima had studied engineering at Tokyo Imperial University. He had worked on aircraft development at Nakajima Aircraft Company before joining military intelligence. He understood aerodynamics, structural engineering, and power plant design. He thought he understood what American industry was capable of producing. Standing before the B-29, he realized he had been wrong about almost everything. The aircraft's skin was smooth, almost mirror-like in places. Japanese bombers had riveted aluminum construction with visible seams and joints. This aircraft's skin appeared nearly seamless, with flush rivets that barely disturbed the aerodynamic profile. The craftsmanship was extraordinary. More than that, it was consistent. Every panel, every joint, every fastener showed the same precision. Japanese engineers opened the forward hatch and climbed inside. What they found would consume them for months. The pressurized cabin stretched the entire length of the fuselage, connected by a crawl tunnel over the bomb bays. Crew members could move from nose to tail without depressurizing the aircraft. At 30,000 feet, where the B-29 operated, outside air temperature dropped to 40 degrees below 0 Fahrenheit. Outside pressure was less than 1/3 of sea level. Crew members needed oxygen to breathe and heating to survive. The B-29 solved these problems with technology Japanese engineers had never successfully implemented. The post-pressurization system maintained cabin pressure equivalent to 8,000 feet altitude, even when the aircraft flew at 30,000 feet. Heating systems kept the interior at survivable temperatures. Crew members worked in shirt sleeves while outside the aluminum skin, the air was thin enough to kill in minutes and cold enough to freeze exposed flesh in seconds. But pressurization was only the beginning. As Japanese technicians explored the aircraft, cataloguing every system and component, they discovered layer upon layer of sophisticated technology. The central fire control system allowed a single gunner to operate multiple turrets simultaneously. The analog computer that controlled the turrets automatically calculated lead angles and deflection. The Norden bombsight in the nose was a precision mechanical computer, using gyroscopes and mirrors to solve differential equations in real time. Every discovery raised the same question: how had American engineers solved these problems? More importantly, how had American factories built these solutions into aircraft rolling off assembly lines at rates Japanese intelligence found difficult to believe? The report stated Boeing's plants in Wichita, Kansas and Renton, Washington were producing B-29 seconds at a combined rate of 100 aircraft per month by late 1944. The engineers worked methodically, documenting everything. They photographed components from multiple angles. They measured dimensions. they sketched mechanical systems. They removed panels to access hidden equipment. What they found consistently defied their expectations. Japan's strategic bombing doctrine in 1944 rested on foundations laid a decade earlier, when the Imperial Japanese Army and Navy competed to develop long-range bomber capabilities. Both services understood that future wars would require striking enemy industrial centers, ports, and military installations far from the front lines. Both invested heavily in bomber development. Neither had created anything remotely comparable to the B-29. The Imperial Japanese Army's heavy bomber in 1944 was the Mitsubishi Ki-67 Hiryu, known to Allied intelligence as Peggy. It was the best bomber Japan produced during the war. First flown in December 1942 and entering service in October 1944, the Hiryu represented the pinnacle of Japanese bomber design philosophy. It carried a crew of 6 to 8 men depending on configuration. Maximum bomb load was 1,760 pounds. Combat radius was approximately 600 miles. Maximum speed at 16,400 feet was 334 miles per hour. Service ceiling was 31,000 feet, though operational ceiling was considerably lower with full combat load. The Hiryu was well designed within its parameters. It had good handling characteristics, reasonable defensive armament, and adequate performance for medium-range bombing missions. Japanese crews praised its reliability and maneuverability. Against the bomber forces of China or the limited fighter opposition encountered in early Pacific campaigns, it was effective. Against American defenses in late 1944, it was marginal at best. The Imperial Japanese Navy's bomber force relied primarily on the Mitsubishi G-4M, Allied codename Betty. This aircraft, which first flew in October 1939 and entered service in April 1941, embodied different design priorities. The Navy demanded extreme range to support operations across the vast Pacific. Mitsubishi's engineers achieved this by minimizing weight wherever possible. The G-4M carried a crew of 7. Maximum bomb load was 2,205 pounds, though typical combat loads were considerably less to preserve range. Maximum speed was 272 miles per hour. Combat radius exceeded 1,500 miles with reduced bomb load. This range capability was remarkable and gave the G-4M strategic reach no other Japanese bomber possessed. But the weight savings that enabled this range came with deadly costs. The G-4M had no armor protection for crew members. Fuel tanks were not self-sealing. Defensive armament was inadequate. When hit by enemy fire, the aircraft burned readily. American pilots called it the flying lighter. Japanese crews called it the flying cigar for its tendency to ignite and burn from end to end. Loss rates were catastrophic. By 1944, G-4M units suffered attrition rates that made sustained operations impossible. Both aircraft represented sophisticated engineering within severe constraints. Japanese designers worked with limited industrial capacity, restricted access to strategic materials, and competing demands from fighter and naval aircraft programs. They created bombers optimized for specific mission profiles against expected opposition. Range mattered more than protection. Maneuverability mattered more than payload. Simplicity mattered more than advanced systems. These design choices made sense in the context of Japan's strategic position and industrial capabilities in the late 1930s. They made less sense as the war progressed and the nature of aerial warfare changed. By 1944, Japanese bombers faced opposition their designers had never anticipated. American fighter aircraft with performance exceeding anything Japanese planners had considered possible. Radar-directed anti-aircraft artillery that could track and engage bombers at altitudes previously considered safe. And American bombers striking Japanese targets with payload capacities and operational ranges that seemed to violate the fundamental trade-offs Japanese engineers understood to govern bomber design. The B-29 program began in January 1940, when the United States Army Air Corps issued a requirement for a hemispheric defense weapon. The specification called for an aircraft capable of carrying 20,000 pounds of bombs for 5,333 miles at a speed of 400 miles per hour. These requirements seemed almost fantasy. No bomber in the world in 1940 could approach this performance. The Army wanted an aircraft that could fly from American bases and strike targets anywhere in the Western Hemisphere, then return without refueling. Boeing's engineers, led by Edward Curtis Wells, submitted a proposal in May 1940. The design was ambitious to the point of recklessness: pressurized crew compartments, remote-controlled defensive armament, 4 engines, each producing over 2,000 horsepower, tricycle landing gear, wing loading higher than any production aircraft. The technical risks were enormous. The costs would be staggering. The Army ordered 2 prototypes in August 1940, then increased the order to 14 aircraft in December before the first prototype had flown. The first B-29 flew on September 21, 1942. Test pilot Eddie Allen took the prototype to 6,000 feet for 75 minutes. The flight revealed promise and problems. The aircraft handled well, and performance projections looked achievable, but engine cooling was inadequate. The Wright R-3350 engines, which were themselves still in development, ran dangerously hot. Fires were frequent. On February 18, 1943, the second prototype caught fire during a test flight. Allen attempted to return to Boeing Field in Seattle. The fire spread. Control systems failed. The aircraft crashed into a meat-packing plant. Allen and his crew of 10 died instantly. 20 workers in the plant died in the subsequent fire and building collapse. The program could have ended there. Instead, the Army accelerated it. In May 1943, orders stood at 1,600 aircraft. Production facilities were under construction in Wichita, Renton, Marietta, Georgia, and Omaha, Nebraska. Suppliers were tooling up to produce components. The military had committed to the B-29 before knowing whether the aircraft's problems could be solved. General Henry Hap Arnold, commanding general of the Army Air Forces, personally drove the program forward. He understood that defeating Japan would require bombing the home islands. The existing bomber force, primarily B-17 seconds and B-24 seconds, lacked the range to operate from any base the United States controlled or could reasonably hope to capture. The B-29 was not merely desirable, it was essential. Without it, strategic bombing of Japan was impossible. Boeing's engineers worked around the clock on solutions. Engine cooling received extensive redesign. Cowl flaps were enlarged and repositioned. Cooling airflow was optimized. Fire suppression systems were improved. The problems diminished but never entirely disappeared. The R-3350 remained a difficult, temperamental engine throughout the war. Mechanics called it a corn cob for its 2 rows of 9 cylinders each. They also called it other things, most unprintable. The first production B-29 flew in September 1943. By December, aircraft were rolling off assembly lines. They went directly to modification centers where hundreds of changes were incorporated. The B-29 was being produced, modified, and introduced to combat simultaneously. Crews trained on aircraft that were still being debugged. Maintenance personnel learned to service systems that were still evolving. The entire program was a calculated gamble that American industrial capacity and engineering talent could solve problems faster than the schedule demanded solutions. The Norden bombsight sat in the bombardier's position in the B-29's nose, and Japanese engineers approached it with something approaching reverence. They had heard rumors of American bombsight technology. Intelligence reports suggested the device was classified at the highest levels, that bombardiers were sworn to secrecy, that the site was destroyed rather than allowed to fall into enemy hands. Now they had one intact. The Mark 15 Norden bombsight weighed about 50 pounds and consisted of over 2,000 precision-machined parts. At its core was a stabilization gyroscope spinning at 8,000 revolutions per minute, maintaining a stable platform regardless of aircraft motion. This gyroscope was coupled to a mechanical analog computer that continuously solved differential equations relating aircraft speed, altitude, wind drift, and ballistic trajectory. The Bombardier input known values. Altitude came from the aircraft's pressure altimeter. Airspeed came from the pitot-static system. Wind direction and speed were estimated from drift observations during the approach. The target's elevation above sea level was determined from maps or previous reconnaissance. Ballistic characteristics of the specific bomb type were set using tables provided for each weapon. With these inputs entered, the bombsight computed the precise moment to release bombs. But it did more than simply calculate. It actively controlled the aircraft during the bomb run. The bombardier looked through the sight's telescope at the target. He turned control knobs to keep the crosshairs centered on the aim point. These movements fed corrections to the autopilot through the pilot direction indicator, a system that converted the bombardier's tracking inputs into heading and airspeed commands. For the final minutes before bomb release, the bombardier flew the aircraft through the bomb site, while the pilot's hands remained off the controls. Japanese engineers disassembled the Norden methodically. They photographed each component. They measured dimensions to tolerances of thousandths of an inch. They analyzed the optical system, which used multiple lenses and prisms to provide magnification ranging from 1.5 times to 22 times. They examined gyroscope mounting, which allowed the stable element to remain level even when the aircraft banked or pitched. They studied the mechanical computer's cam mechanisms, gear trains, and differential systems that performed continuous calculations. What impressed them most was not the theoretical elegance of the design. Japanese engineers could understand the mathematics and physics underlying the bombsight's operation. What stunned them was the manufacturing precision required to build such a device, and the fact that American factories were producing them in quantity. The gyroscope alone required machining tolerances and balancing precision beyond what most Japanese factories could achieve in laboratory conditions. The Norden incorporated this component as a standard production part. The optical elements required grinding and polishing glass to optical quality, then assembling multiple elements into compound lenses with precise alignment. The mechanical computer required gears cut to, accuracies measured in 10,000ths of an inch, cams shaped to mathematical curves with minimal error, and bearings that maintained these tolerances under vibration and temperature extremes. Every Norden bombsight required hundreds of hours of skilled labor by precision instrument makers working to standards that exceeded normal aircraft production by orders of magnitude. Japanese bombing methods relied on different principles. Level bombing used simple mechanical sights that required the bombardier to estimate wind drift and trajectory manually. The bombardier watched the target approach, made mental calculations based on training and experience, and released bombs at what he judged to be the correct moment. Accuracy depended entirely on the bombardier's skill. In practice, this meant bombs fell in patterns hundreds of yards across. Hitting a specific building was unlikely. Hitting a general area, such as a harbour or factory district, was achievable with enough aircraft dropping, enough bombs. Dive bombing offered better accuracy by reducing the time bombs spent in free fall. Aircraft dove at steep angles toward the target, released bombs at lower altitudes, then pulled up. The shorter fall time meant wind had less time to drift bombs off course, and the steeper trajectory reduced horizontal dispersion. But dive bombing required specialized aircraft, subjected crews to high G-forces during pull-out, and exposed aircraft to intense anti-aircraft fire at low altitudes. It was primarily a naval tactic, used against ships where precision mattered more than the risks. The B-29's bombing system represented a completely different philosophy. The Norden removed human judgment from the release decision. Once the bombardier had input the parameters and begun tracking the target, the bombsight calculated the release point with mechanical precision. Human error in estimating wind drift or trajectory was eliminated. The bombardier's skill mattered in target identification and tracking, but the release timing was calculated, not estimated. More significantly, the entire system was designed for high-altitude bombing. The B-29 operated at altitudes where Japanese fighters struggled to intercept and anti-aircraft fire was less effective. At 30,000 feet, the aircraft was difficult to see from the ground and moving fast enough that optical gun sights could not track it effectively. The crew worked in pressurized comfort, while the bombardier used magnified optics to identify and track targets from 6 miles above. The central fire control system occupied the minds of Japanese engineers for weeks. They had never seen anything like it. The B-29 carried 12 50-caliber Browning M2 machine guns in 5 turret positions, 2 guns in the upper forward turret just behind the cockpit, 2 guns in the upper aft turret behind the wing, 2 guns in the lower forward turret beneath the fuselage, 2 guns in the lower aft turret, 2 guns in the tail turret, which also mounted a single 20mm cannon, standard defensive armament for a heavy bomber. But the system controlling these weapons was revolutionary. 4 gunner stations controlled all turrets except the tail. Each gunner sat at a station with a computing gun sight. The gunner looked through the sight at attacking fighters, tracked the target, and pressed the trigger. The system automatically selected which turret had the best firing position, aimed that turret at the target while calculating lead angle and deflection, and fired the guns when the solution was correct. The computing gun sight used mechanical and electrical systems to solve the gunnery problem continuously. Range to target came from the gunner's range estimation dial. The gunner tracked the attacking fighter, keeping it centered in the sight. The system measured the angular rate of change as the gunner tracked the target. Combined with range, this gave target velocity relative to the bomber. An analog computer calculated the lead angle required to put bullets where the target would be when they arrived, not where it was when the gunner fired. The turrets themselves were electrically powered and hydraulically controlled. The gunner's tracking inputs moved the turret smoothly and precisely. Traverse rates exceeded 100 degrees per second, fast enough to track fighters in turning attacks. The turrets were linked. Multiple gunners could control the same turret, but only one at a time. If a fighter attacked from a position where both the upper forward and lower forward gunners could engage, both could track it through their sights. The system automatically assigned turret control to the gunner with the better firing position. This eliminated the traditional problem of heavy bomber defense. In a B-17 or B-24, each gunner operated a single station with limited field of fire. Gunners had to coordinate to avoid gaps in coverage. If a fighter attacked from a blind spot between positions, it could approach unmolested until entering another gunner's field of fire. The B-29's system meant every attack came under fire from optimally positioned turrets controlled by gunners who could focus on tracking rather than manual turret operation. Japanese engineers examined the turrets in minute detail. The electric motors that traversed and elevated the guns, the hydraulic systems that absorbed recoil, the ammunition feed systems that reliably delivered belts of 50-caliber rounds, even during violent maneuvers. The computing mechanisms in each sight, the electrical systems that transmitted control signals from sights to turrets, the interlocks that prevented gunners from shooting off their own aircraft's tail or wings. Every component reflected design sophistication and manufacturing quality beyond what Japanese industry could replicate. The electric motors were precisely balanced and thermally protected. The hydraulic components were machined to tolerances that prevented leaks under pressure. The ammunition feeds used spring-loaded mechanisms that compensated for belt tension during firing. The computing sites incorporated dozens of precision parts working in coordination. But again, what stunned Japanese engineers was not the theoretical design, but the practical implementation. General Electric had designed and manufactured these systems in production quantities. Every B-29 had 4 of these sophisticated computing gun sights, plus simpler sights for the tail gunner. The turrets, the motors, the hydraulics, the ammunition feeds, all were standard production items installed on assembly lines by workers who might never have seen the inside of an aircraft before the war. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The contrast with Japanese bomber defensive armament was stark. The G4M Betty carried 5 machine guns, operated manually by individual gunners. The dorsal turret had a single 7.7mm machine gun, a weapon firing rounds identical to rifle ammunition. Side gunners operated another 7.7mm gun from beam positions. A ventral gunner manned a similar weapon in a retractable turret. The tail position carried a 20mm cannon, the only heavy weapon on the aircraft. Colonel Nakajima compiled his preliminary report in December 1944 after 6 weeks of intensive examination. The document ran to over 200 pages with photographs, technical drawings, and detailed specifications. His conclusions were disturbing enough that he requested a face-to-face briefing with Army Technical Research Institute leadership rather than submitting the report through normal channels. The meeting took place on December 28 in Tokyo. Nakajima presented his findings to a room of senior technical officers and industrial representatives. He began with physical specifications. The B-29 weighed 105,000 pounds empty and could take off at weights exceeding 140,000 pounds. Maximum bomb load was 20,000 pounds, though typical combat loads were 12,000 pounds to preserve range. Combat radius exceeded 1,500 miles with standard fuel load. Ferry range with minimal bomb load and maximum fuel exceeded 5,000 miles. These numbers were sobering but comprehensible. Japanese engineers could understand an aircraft optimized for payload and range at the expense of other characteristics. What came next was harder to process. Nakajima described the pressurization system in detail. The cabin pressure differential of 8 pounds per square inch, the multi-stage compressors driven by engine bleed air, the pressure regulators and safety valves, the heated pressurized crew stations connected by the tunnel over the bomb bays. He explained that this system allowed the B-29 to operate routinely at altitudes where Japanese fighters struggled. The Nakajima Ki-84 Hayate, Japan's best fighter in late 1944, had a service ceiling of 34,400 feet, but this was maximum ceiling under ideal conditions with a clean aircraft. Combat ceiling with full fuel and ammunition was several thousand feet lower. The fighter's rate of climb at altitude was marginal. Intercepting a B-29 at 30,000 feet required the Ki-84 to climb for 20 minutes or more, consuming fuel and arriving with limited time for combat before having to descend. Meanwhile, the B-29 crew worked in shirt-sleeve comfort. The heating system maintained cabin temperature at 70 degrees Fahrenheit. Crew members did not require heavy flight suits or heated clothing. They were not fatigued by cold or hypoxia. They could focus entirely on their tasks during missions lasting 12 to 15 hours. Nakajima moved to the defensive armament system. He displayed photographs of the computing gun sites and described their operation. He explained how a single gunner could control multiple turrets. He detailed the automatic lead computation and turret selection. The officers in the room were silent. Several asked detailed questions about the mechanical computers. How did they calculate deflection? What inputs did they use? How were they calibrated? Then Nakajima reached the Norden bombsight. He described its precision, its integration with the autopilot, its manufacturing quality. He showed photographs of the disassembled site with components laid out and measured. He explained that American crews bombed from altitudes above 30,000 feet, using this device to place bombs within hundreds of feet of aim points. Not sometimes. Routinely. The site's theoretical accuracy was within 75 feet from 30,000 feet under ideal conditions. One officer objected. This could not be correct. Bombing accuracy from such altitude was impossible. Wind drift alone would scatter bombs across hundreds of yards. Nakajima acknowledged that actual combat accuracy was less than theoretical maximum. Weather affected results. Bombardier skill mattered. Target identification at high altitude was difficult. but American crews were achieving accuracies that Japanese bombing methods could not match even from medium altitudes with clear visibility. The room remained quiet as Nakajima reached his conclusions. The B-29 represented not an incremental improvement over existing bombers, but a generational leap in capability. Every system, from pressurization to defensive armament to bombing accuracy to range and payload, exceeded Japanese capabilities by margins that could not be closed through improved training or tactical innovation. The aircraft itself was formidable, but more concerning was what it revealed about American industrial capacity and engineering sophistication. The Norden bombsight alone required manufacturing precision beyond what most Japanese factories could achieve. Yet American industry was producing them in quantities sufficient to equip every B-29. The pressurization system required complex engineering and precise assembly. American factories installed these systems on production lines. The defensive armament system incorporated computing technology Japanese engineers understood in theory, but could not manufacture reliably. American contractors supplied them as standard equipment. Nakajima's report circulated through Japanese military and industrial leadership in early 1945. The conclusions were inescapable but difficult to accept. Japan could not build an aircraft comparable to the B-29. The technological gap was too wide. The industrial capacity required was too great. The time needed to develop equivalent systems was too long. Even if Japanese engineers could design comparable systems, which many doubted, Japanese factories could not manufacture them in meaningful quantities. The Nakajima Aircraft Company, Japan's largest aircraft manufacturer, attempted to design a pressurized heavy bomber. The G-10N Fugaku project aimed to create a bomber capable of reaching the American mainland from Japanese bases. Design specifications called for a 6-engine aircraft with pressurized crew compartments, range exceeding 7,000 miles, and bomb load of 44,000 pounds. The project never progressed beyond preliminary design studies. The engineering challenges were enormous. The industrial resources required were simply unavailable. Mitsubishi Heavy Industries examined the possibility of license-building Wright R-3350 engines using technical data from the captured B-29. Engineers quickly determined this was impossible. The R-3350 required aluminum alloys Japan could not produce in sufficient quantity or quality. The precision machining for cylinders, pistons, and crankshafts exceeded Japanese manufacturing capabilities. The superchargers required materials and metallurgy Japan had not mastered. Even the spark plugs presented problems. American plugs used electrode materials and ceramic insulators superior to anything Japanese suppliers could provide. Some Japanese engineers proposed simpler approaches. Perhaps Japan could not match the B-29's sophistication, but could Japanese industry produce a less capable heavy bomber in useful numbers? A bomber without pressurization, with simpler defensive armament, with less advanced bomb sights, but with sufficient range and payload to strike distant targets? Studies concluded even this was beyond Japanese capacity in 1945. Aluminum was increasingly scarce as American submarines cut off bauxite shipments from Southeast Asia. Aviation fuel production was declining as refineries were bombed and raw material supplies dwindled. Machine tools were wearing out faster than they could be replaced. Skilled workers were being drafted to replace military casualties. Factories were being dispersed to avoid bombing, reducing efficiency. The industrial system that had built Japan's pre-war air force was collapsing under the accumulated strain of years of total war. Meanwhile, B-29 seconds appeared over Japan in increasing numbers. The first raid on Tokyo from the Marianas came on November 24, 1944, just days before the captured aircraft landed in Manchuria. That raid involved 111 B-29 seconds. By March 1945, raids involved over 300 aircraft. By May, raids of 500 or more B-29 seconds were routine. The bombers came in daylight and at night. They struck from high altitude with precision bombs and from low altitude with incendiaries. Japanese air defenses could not stop them. Fighter interceptions were attempted but proved costly and largely ineffective. The B-29's defensive armament was formidable. Its speed at altitude, over 350 miles per hour, was faster than most Japanese fighters could maintain at 30,000 feet. Its operating altitude forced fighters to climb for extended periods, arriving with limited fuel for combat. When fighters did intercept successfully, the casualties were heavy on both sides. The B-29 was not invulnerable, but destroying one required commitment and courage that often resulted in the attacking fighter being shot down. Anti-aircraft artillery was similarly ineffective. Japanese heavy anti-aircraft guns could reach 30,000 feet, but fire control systems could not reliably track fast-moving targets at extreme altitude. Barrage fire consumed ammunition without achieving hits. Predicted fire based on visual tracking could not compensate for the bomber's speed and altitude. The B-29 seconds flew through flak and continued to their targets largely untouched. Japanese civilians in cities targeted by B-29 raids experienced the war's industrial disparities most directly. The incendiary raids on Tokyo in March 1945 created firestorms that killed approximately 100,000 people in a single night. The physical destruction exceeded anything experienced in European cities, except perhaps Dresden and Hamburg. Square miles of urban area were reduced to ash. Hundreds of thousands were left homeless. Industrial production in affected areas ceased entirely. The psychological impact was devastating. Japanese propaganda had assured civilians that American bombers would never reach the home islands. When raids began, propaganda insisted the attacks would be stopped by superior Japanese fighting spirit and defensive preparations. By mid-1945, no one believed this. The B-29 seconds came when they chose, struck what they chose, and departed largely unmolested. The reality was visible in the burning cities and mounting casualties. The captured B-29 Manchuria ended up in Soviet hands through circumstances that revealed another layer of technological disparity. In early 1945, as the Soviet Union prepared to enter the war against Japan, Soviet technical intelligence became aware of the aircraft. Through diplomatic channels and military coordination, arrangements were made to transfer the B-29 to Soviet custody. 3 more B-29 seconds that had made emergency landings in Soviet territory after missions against Japan were also retained by the Soviets despite American requests for their return. Soviet engineers examined these aircraft with the same intense interest Japanese engineers had shown. Soviet conclusions were different. The Soviet Union had the industrial capacity and technical sophistication to reverse engineer the B-29. Stalin ordered the aircraft copied exactly, down to the smallest detail. The project was assigned to Andrei Tupolev, the Soviet Union's premier aircraft designer, who was at the time imprisoned in a sharashka, a special prison for technical experts who worked on state projects. The resulting aircraft, designated Tu-4, was an exact copy of the B-29. Soviet factories manufactured every component from measurements and analysis of the captured aircraft. This required extraordinary effort. Over 105,000 engineering drawings were produced. 900 factories participated in manufacturing components. New materials had to be developed. New manufacturing processes had to be created. The first Tu-4 flew in May 1947. By the early 1950s, the Soviet Union had produced over 1,000 Tu-4 bombers, giving Stalin a strategic bombing capability comparable to the American B-29 force. The fact that the Soviet Union could reverse engineer and mass-produce the B-29, while Japan could barely contemplate the attempt, illustrated the fundamental differences in industrial capacity and technological sophistication. The Soviet Union in the immediate post-war period had an industrial base damaged by 4 years of devastating warfare. Entire cities had been destroyed. Factories had been evacuated, dismantled, and relocated. Millions of skilled workers had been killed. Yet Soviet industry could still accomplish what Japanese industry at its pre-war peak could not. Japanese engineers who had examined the captured B-29 learned of the Soviet Tu-4 program after the war. For many, it confirmed what they had concluded in 1945. The technological gap between Japan and the Western industrial powers was not a matter of specific innovations or individual pieces of equipment. It was systemic. It reflected differences in industrial capacity, manufacturing precision, materials science, and engineering education that had accumulated over decades. Some Japanese engineers who had worked on the B-29 examination went on to rebuild Japan's post-war aviation industry. They applied lessons learned from studying American technology. They understood that matching Western technology required not just clever design, but systematic improvement in manufacturing quality, materials, science, and engineering standards. Japanese aircraft industry that emerged in the 1950s and 1960s reflected this understanding, emphasizing quality control and manufacturing precision as much as design innovation. The cultural impact of the B-29 on Japanese collective memory was profound and lasting. The bomber became a symbol of American technological and industrial supremacy. The term B-29 entered Japanese vocabulary as shorthand for overwhelming power and unstoppable force. Survivors of the bombing campaigns remembered the aircraft with a mixture of fear and reluctant respect. The sound of the R-3350 engines became associated with destruction and helplessness in the face of superior force. American aircrews who flew B-29 missions against Japan had different perspectives. They experienced the aircraft as a remarkable but temperamental machine. The R-3350 engines remained problematic throughout the war, requiring careful management and frequent maintenance. The pressurization systems leaked and required constant monitoring. The defensive armament systems were sophisticated but could malfunction. Combat losses were significant despite the aircraft's advantages. On the March 9th to 10th, 1945 raid on Tokyo, 14 B-29 seconds were lost to Japanese defenses and operational failures. The captured B-29 that Japanese engineers examined in Manchuria represented more than advanced technology. It represented the culmination of choices made years earlier about industrial priorities, resource allocation, and the nature of modern warfare. The United States had committed to strategic bombing as a primary offensive method and built the industrial capacity to execute that strategy. Factories were constructed specifically to produce heavy bombers. Supply chains were organized to deliver materials. Training programs were established to produce crews. Research programs developed the specialized technology these aircraft required. Japan had made different choices based on different strategic circumstances. Naval aviation received priority because Japan was an island nation dependent on maritime communications. Fighter aircraft received emphasis because Japan anticipated defensive operations. Bombers were secondary. Heavy bombers requiring years of development and enormous industrial resources were luxuries Japan could not afford. These choices were rational given Japan's strategic position and industrial capacity in the 1930s. But by 1944, those earlier choices constrained Japan's options. The industrial capacity that might have produced heavy bombers was instead committed to fighters, to naval aircraft, to replacing losses at a rate that exceeded sustainable production. Factories were bombed. Raw materials were embargoed. Shipping was sunk. The industrial system slowly collapsed under pressures it was never designed to withstand. The engineers examining the B-29 understood they were looking at the product of an industrial system, an order of magnitude more capable than Japan's. The Norden bombsight was not simply a clever mechanism. It was the output of a system that could design, manufacture, and produce in quantity devices requiring thousands of precision parts, machined to tolerances most Japanese factories could not achieve. The pressurization system was not just sophisticated engineering. It was proof of an industrial base that could incorporate complex systems into production aircraft as standard equipment. Every system in the B-29 told the same story. American industry could produce in quantity what Japanese industry could barely produce at all. American engineering could solve problems Japanese engineers recognized but could not address. American resources could support programs that Japanese resources could not sustain. The gap was not in intelligence or dedication or theoretical understanding. Japanese engineers were highly educated and creative. The gap was in industrial capacity, accumulated technological expertise, and access to materials. The morning Colonel Nakajima first walked around the captured B-29, he had believed he understood American capabilities. He had studied intelligence reports on American aircraft. He had examined wreckage from previous encounters. He thought the differences were matters of degree, not kind. After 6 weeks of intensive examination, he understood differently. The technological gap was generational. Japan was fighting an industrial power that operated on fundamentally different scales of production and sophistication. This realization was sobering but not entirely new. Japanese naval officers had reached similar conclusions after examining captured American naval equipment. Japanese soldiers had observed the abundance of American supplies and equipment compared to Japanese scarcity. What made the B-29 examination significant was its systematization of these observations into technical documentation. The report provided quantifiable proof that Japan's industrial capacity could not match American production in quality or quantity. The legacy of the B-29 the Pacific War was thus dual. It was a weapon that brought destruction to Japanese cities and contributed directly to Japan's defeat. But it was also evidence of industrial disparities that shaped the war's outcome as much as any battle. The young Japanese engineer, standing in the muddy Manchurian airfield in November 1944, looking at an aircraft his nation could never build, was witnessing not just a machine, but the material reality of total war between industrial powers of vastly different capabilities. The B-29 that Japanese engineers could not believe existed, with its bombsight technology that seemed impossible, and its systems that reflected manufacturing precision beyond Japanese capacity, was not an aberration, it was representative. Every aspect of American military production, from small arms to ships to vehicles to aircraft, reflected similar advantages in scale and sophistication. The captured bomber was simply the most dramatic and concentrated example of differences that permeated every level of industrial warfare. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.